Okay, so in this chapter, we'll continue talking about some techniques for integration. And so far, we've seen substitution, right, as a way for us to reverse the chain rule for differentiation, right, by making that u substitution and transforming our integral. Here, we're going to talk about another technique called integration by parts. And to start us off here, let's consider this integral of x cosine x plus sine x dx. Remember that when we're evaluating integrals, we're looking for basically antiderivative of the function, right? So sine x, that's an easy integral. We know sine x just gives you minus cos x as its antiderivative, right? But what do we do about x times cosine x? That's not as obvious. Instead, we notice here that x cosine x plus sine x looks kind of suspicious to me. In the sense that if I put a 1 here beside sine x, this should remind you of something you've seen in differential calculus. Right? Do you remember what it is? This is actually the derivative of the product of x and sine x. If you take x to be f and sine x to be g, then by the product rule, the derivative is f prime times g plus f times g prime. Therefore, what this allows me to do is to just go straight to x sine x plus c as the antiderivative of this integral. And notice what happened there. Sine x was easy to deal with, right? X cosine x was not. But we were able to deal with x cosine x by treating it together with sine x and thinking about the product rule. And so this was hard, this was easy. What if I ask you the following question instead? What if it was x cosine x by itself? So now we don't have sine x beside it. However, if you again look at this statement I have up here, I can basically rewrite this, or even the statement with the product rule, right? I can rewrite that to be the following. I can say the integral of x cosine x dx is equal to x sine x minus the integral of sine x dx. Okay, again, where did I get this? From this statement up here, right? I basically take the integral of sine x, that easy part, and bring it to the right. And what is this telling me now? It's telling me that this difficult integral can actually be written in terms of this easy integral, plus some other function, which doesn't have an integral anymore. So we're good there. But now, I can write this as x sine x plus cosine x plus c. Right, and what this actually gave me here was now the antiderivative of x times cosine x. Which again, if you remember, was hard for us at the beginning, but became easy once we used the product rule, or essentially what is the reverse of the product rule. And it's easy to check your work here. If you take the derivative of your answer, well, you'll see the product rule here again in action, right? It's x cosine x plus sine x. Cosine x becomes minus sine x. Then they cancel, leaving you with just x cosine x, which is correct. So let's systematize this a bit. The product rule tells us, again, that f times g is equal to f prime times g plus f times g prime, right? Or the derivative of f times g, right? This f prime g plus f g prime. And so writing this as an equation with integrals instead, we can say fx gx, right? F of x times g of x is the integral f prime of x g of x dx plus the integral of f of x g prime of x dx. And so just moving one of these integrals over to the left, right, or rearranging, we end up with this statement. Essentially saying that if you have an integral, right, that you can view as the product of two functions, where the second function is the derivative of g, well, you can actually rewrite everything here as f times g minus the integral of, well, it's still going to be f and g inside, but now the prime has moved, right, to f, with the goal of coming from a difficult integral to something that's now easy to deal with. Okay, so let's work on an example. Evaluate the integral x times e to the 2x. Right, and I'll write the formula on this page so you can refer to it. F g prime, I'll write it completely here, f of x g prime of x dx is equal to f of x g prime of x minus integral of f prime of x gx dx. And I'll actually give you sort of a shorter way to write this integration by parts formula. Some people actually write this as u, or I would say most people write this as follows: u equals f of x, dv equals g prime of x dx, viewing this as u and this as dv. And so this gives you du equals f prime of x dx, and v equals g of x. And now I can actually write this as u dv equals uv minus the integral of v du. And that rolls off the tongue a bit faster there, and a bit better. But the idea is the same, right? You're deciding in the integral that you're given how to pick u and dv so that when you use this integration by parts formula, and you have now du and v, right? So it's v du, you get something easier to evaluate, right? So that's always the goal here. Okay, so here we have a couple of options, right? I can pick u to be, so I have two terms, x and e to the 2x. So why don't we try picking u equals e to the 2x and dv to be whatever's left, x dx, right? So this is the same thing as saying f of x is e to the 2x and g prime of x is x. In order to use this formula, well, I need v. Well, what's v here? It's the integral of dv, right? So the antiderivative is 1/2 x squared. U is e to the 2x, which means du is 2e to the 2x dx. And now using this formula, it's going to give me u times v minus the integral of v times du. Okay, and you probably noticed something here. This integral is actually even more complex, right? Even more complicated than the integral we started with. We started with a linear function times an exponential function. Now the linear function is a quadratic, and we're still multiplying by an exponential. Well, it got harder to evaluate. What this tells me is our choice for u and dv was the wrong choice. So let's do it again. But now picking u equals x instead, and dv equals e to the 2x dx. U equals x gives me du equals dx, right? Because x is just 1 as its derivative, and then v is now 1/2 e to the 2x dx. So same thing, it's the exact same formula, u times v, x times 1/2 e to the 2x minus the integral of v, oh sorry, this shouldn't have a dx here. V is 1/2 e to the 2x, du is just dx. Okay, so this is actually what we want. Because now this is just a simple integral. One-fourth e to the 2x plus c. Right? And again, you can check your work here. If you take the derivative, you should get this original function back, x times e to the 2x. Right? But you see what's happening here. Right? Your choice of u and dv actually makes a huge difference in the integral that you're going to get, or that you're going to end up with. In fact, both of what I did here, they're mathematically correct, both of them. It's just that what I did in the second part actually got us somewhere in terms of getting the antiderivative, right, of the integral that we started with. Whereas here, we wouldn't have gotten anywhere. And in general, a good rule of thumb to think about is that since u and dv are what we start with, and we're ending up with du and v in the new integral, you want to pick u to be generally that function that becomes easier when you take its derivative. That's why polynomials really work well, right? Because what happens when you take derivatives of polynomials? The degree goes down, right? They become simpler and easier to deal with. And let's do one last example here. The integral of ln x times dx. And maybe you're a bit confused here. Maybe you say, well, I only see one term here. How am I going to pick a u and a dv if I only see one term there? It's just a ln x. Well, why don't we pick u equals ln x? Well, that's my option here. And why don't I pick dv to just be dx? Right? So you can think of this as ln x being multiplied by 1 dx. So 1 times dx is my dv. So we do the same thing, right? From u, we compute du, we compute v from dv. So v equals x now, take the antiderivative, and du equals 1 over x dx. This integral now becomes, using this integration by parts formula, is u times v minus the integral of v times du. Aha! X times 1 over x cancel, it just leaves me with the integral of dx. Wow, and that's so much easier. Right? From the integral of ln, that's just the integral of 1. It's just simply 1. So it's x ln x minus x, and then I can add my plus c at the very end. Right? So if you see a logarithm, that's going to be a nice candidate for you, right? Because when you take the derivative of the logarithm, it just becomes 1 over x, right? So the log disappears from your integrand.